Hi there. While moving and rearranging my lab, I stumbled over this rather big and very heavy device I got a long time ago from eBay but never used. I put it on the bench to decide whether to keep it or get rid of it. It's an appliance safety tester. Don't confuse it with a similar looking Clark flash tester I showed a while ago and still have. This unit is supposed to be transportable to sites. It has a carry handle on one side and a leather pouch on the back for cables and such. In my case, it contains the TheHWcave power cord, which is fixed to the unit, a black wire for earth bonding tests that I actually made myself. It wasn't part of the unit. It's 4 mm square and has a really low resistance, and a high voltage probe on a cable, again permanently fixed to the unit. For safety reasons, the probe has a plunger on the rear that needs to be pressed and kept down for the metal tip to come out. The front states that this is model TEM 4700, and I found sources that claim it's made by Tech, not Tektronix, mind you. No idea who Tech is and if that's true. I found zero documentation on this unit. No manual, no spec sheet, nothing. But with some knowledge of pad testing, it should be possible to work out how to use it by carefully examining the controls and sockets on the front plate. So let's do that. Part of these tests is to check if the appliance is properly earthed, and here we have two sockets for earth return, one labeled soft and the other normal. The soft one should be seen in the light that the earth test purposely uses high currents to flush out weak earth connections. Fine for toasters and kettles and the like, but modern low power electronic equipments are generally not designed for such currents. The soft socket probably provides a test with lower current. The front has two power sockets. The white one is a standard TheHWcave socket for 230 volts AC. The one under the orange cover is a socket for 110 volts, which is occasionally used for electrical tools on construction sites because it reduces the risk of electrocution if the leads are accidentally cut or damaged. So this tester can be used for either 230 volts AC or 110 volts AC equipment. In the middle we have a rotary button with 6 positions. The top 3 are for class 1 equipment. Basically that's stuff that has a proper earth connection like a toaster or kettle, and all metal parts should be connected to earth. The lower 3 are for class 2 or doubly insulated equipment like USB chargers that are in a plastic housing and have no earth connection. In either case, the most left position is the soft test and it gets tougher on the other settings. However, let's pause a moment and examine the writing. Class 1 soft test uses 500 volts for an insulation test. That's what modern pad testers use as well. But the other two class 1 settings use 1250 volts. That's more than double what modern testers do. And there are 2 numbers on each class 1 position, an ohm value and a voltage. This means this tester does 2 tests, testing how good the earth connection is in terms of its resistance, and a high voltage insulation test. Class 2 doesn't have an earth connection, so there is no test for that, only for high voltage insulation. And boy, even the soft test uses 2500 volts. The position labeled routine ups that to 3000 volts and the normal position to 3750 volts. And these are all AC RMS values, so the peak voltage at 3750 volts is almost 5300 volts. Wow! Even soft will very likely destroy whatever modern equipment you plug into here. Was this machine built for a different standard, or maybe an older standard? If anyone knows, please leave a comment. As far as operation, there is set rotary button and a push button below that's labeled test. That's it. I suppose the results are shown with the 3 lamps above. 2 red ones if either earth resistance or insulation test failed, and a green one if everything passed. On the most left we have an ohm meter. The green area goes to 0.1 ohm, the orange zone to 0.5 ohm, and everything above 0.5 ohms is red, with the most right position marked inf for infinity. As with most analog multimeters with an ohm range, there is a rotary control marked setInf, where you need to set the instrument to show infinity while no resistance is measured. Finally, there are two lamps labeled mains. One shows whether the unit is on and the other one shows false. This was rather tedious, sorry, but at least gives an idea what this unit does, if it works. Let's plug the power cord in. Because there is no power switch, the on lights up immediately. At least the fault light doesn't illuminate, which is encouraging. With nothing connected to the sockets on the front panel, let's run some tests. First, going to the class 2 settings. I expect all these to pass, showing a green light, because the only test is insulation, and with nothing connected there should be no problems in passing, unless there would be an insulation fault inside the tester itself. In a similar way, I expect all the tests for class 1 to fail with an earth fault, as the unit cannot find an earth connection. The meter is deep in the red zone, but not quite at infinity as it should, so that will need to be adjusted, but so far the tester seems to work as it should. As I mentioned, with nothing connected, class 1 test should show an infinite earth resistance. It isn't at the moment, but that is easy to correct. I expect this will have to be checked and corrected periodically, as the setting probably depends on the value of the ever-fluctuating mains voltage. As this tester is likely destructive to most modern equipment, I decided to use a little box I made some time ago, which provides a convenient and safe way to connect probes to main voltage. You can buy these ready-made, but where's the fun in that? The box simply connects each of the 3 wires in a mains lead to a shrouded banana safety socket. Green is earth, blue is neutral, and the yellow one is live and should really be brown, but I did not have a brown one at the time, and it has been yellow for years now. The other end goes into a standard UK mains plug, nothing special. Now that I opened it, the cable I used is a 0.75mm square, and that's certainly not rated for 13 amps. The problem is that you buy these mains plug, they all come with a 13 amp fuse pre-installed. My bad for not changing it. Well, no time like the present. Out with a 13 amp fuse and a more appropriate 5 amp fuse in. For my box you can see I have tons of 13 amp fuses because, as I said, every plug comes with it, and unless it's for a toaster, kettle or floor heater, the fuse should be changed. Oh well, at least it's done now, continuing with the main program. Let's plug the unit in and do a class 1 soft test. It still fails because the earth return is missing. The tester wants to measure the resistance of the earth wire in my box, and while it has access to the earth terminal in the front panel socket, it also needs to have a connection to something that should be earthed on the device under test. In this instance, the only thing available is the green socket. Running the test and the green light comes on, so we pass the earth test and the insulation test. Note that the meter did not show anything for soft tests. Moving on to a proper test, but for items with long leads, for example a vacuum cleaner. I think the tester will treat any resistance below 0.5 ohm, basically anything not in the red zone, as okay for this test. It passes and the meter shows about 0.05 ohm, still well into the green zone. Moving to the normal setting, this reduces the tolerance to 0.1 ohm, basically the green zone only. And it fails. The meter still shows we are well in the green zone, so it should not fail. Not sure what's going on there. Maybe the unit needs to be recalibrated. I noticed that my white cable and the UK plug are quite warm already. How much current did the tester use for these tests? A clump meter across the earth return will tell. Any bets? Wow, 33 amps in the normal setting. I did not think it was that high, but now I understand that my 0.75mm square white mains cable is getting pretty hot. There is no automatic stop. The current flows as long as I keep the button pressed. How about the long lead setting? It's the same, 33 amps, no difference. And for the soft setting? Only 10 amps. That's really soft compared to the others. But the voltage used for the earth resistance measurement is actually quite small, just 8 volts AC. Okay, that was the earth resistant part of class 1 tests. Onwards to insulation. On class 1, live and neutral are shortened and high voltage is applied between these and earth. To measure it, I use this impressive high voltage probe rated for 40,000 volts. it divides by 1000, so 1000 volts shows as 1 volt on the multimeter. The low voltage outputs are connected to the meter, while one of the high voltage inputs is connected to the earth terminal of my box, and I use the probe to check the live or neutral sockets. That's not ideal because the tip is too wide to really connect. Let's see how we get on. Using class 1 soft settings, I should see about 500 volts or 0.5 volts after the division by 1000, and indeed that's about what's there. How about the long lead setting? I added a banana plug tip into the live socket to make probing a bit easier. Okay, we should see 1250 volts and it shows 1224, not bad. Onwards to normal setting, and nothing. Because we still have the earth fault, that shouldn't be there. At least now I know that the unit first tests for earth faults, and if that fails, it does not proceed to insulation testing, which is very sensible given the safety implications. For class 2 there is no earth, so the high voltage is applied between the shortened live and neutral terminals and the separate high voltage probe. You are supposed to use that probe to poke the device under test. For example, you would touch the metal part of a USB connector in a USB charger. Sounds like fun? I don't know. Well, let's first measure what we get in class 2 tests. I rather use only one hand with my 40 kV rated probe, so I make my life easier by using a rubber band to force the tester probe tip to be exposed all the time. Starting with the soft test, only about 1900 volts, not 2500. No doubt 1900 is plenty, but let's see if the others are also falling short. Indeed, the routine setting is only 2500 volts when it was labeled 3000, and the normal setting is only about 3400 volts instead of 3750. I still think these are way too high for using as a pad tester with today's devices, but I would be interested if there's something not right or if this tester was tamed down a bit. Just for fun, in the class 2 normal setting, does 3400 volts produce a spark through the air? Sure does. And a piece of paper? Yes, not a good insulator. With the lab lights partially off, the flash looks a little bit more impressive. Okay, fun is over. Time to look inside and see how it works and if we can do adjustments. After removing 6 screws, the lid, a solid piece of metal, can be lifted off. It looks remarkably clean because there are no vents letting dust in. The inside looks mostly electrical rather than electronical, but there is one PCB. On the far right we have the wire going to the high voltage probe for class 2 devices. This comes directly from the most right transformer. This is interesting because it means that the high voltage for class 1 is done elsewhere. There are 3 trim ports for calibrating the class 1 earth resistance measurements on the PCB, but there is nothing similar for the high voltage insulation measurements. It comes directly from transformers out of the mains voltage. This means the value will fluctuate, which could explain why the class 2 measurements were lower than expected. There are 2 50-watt power resistors mounted on the bottom. The left one is marked R68, that is 0.68 ohms, and connects to the earth soft return. The right one is 0.1 ohm and connects to the normal earth return socket. The other ends of the 2 resistors are connected and go to a transformer which is hidden under the PCB, and to a white wire which ultimately goes to the meter and the PCB. The normal earth return is also connected to a thin green wire, and the soft return has a thin yellow wire which is again a bit hidden. Here you can see that the live and neutral of both front panel sockets are permanently shortened together with a red wire. The earth terminals of both sockets are connected using very thick wire and go to the central earthing point. Since there are trim ports for the earth resistance measurements, I want to check and fix the calibration of the class 1 normal setting. It should not show fault when the resistance is in the green area, that is below 0.1 ohm. For that, I thought I'd use a 0.1 ohm resistor as a reference, which you see here attached to the green terminal of my test rig. This turned out to be a bad idea. If you recall, before adding the resistor, the reading was about halfway into the green zone, or about 0.05 ohms. With the additional 0.1 ohm resistor in series, the value should be 0.15, and indeed it is now in the orange zone, halfway between 0.1 and the tiny 0.2. Great, so the measurement is accurate. But why is this a bad idea? If you would have been in the room, you would have noticed the bad smell of overcooked resistor. That poor 0.1 ohm ceramic resistor is rated for 3 watts. With 32 amps flowing through it, it dropped of course 3.2 volts, and 3.2 volts times 32 amps means it was loaded with 102 watts. You have seen how long I used it, and in that short time it is now literally toast. Even though it still looks okay, it's for the bin. What's the alternative? I don't have any resistors suitable for these tests, but instead of a resistor and my super low resistance earth return wire, I can replace both with a much longer and thinner return wire instead. That wire distributes the heat if I only do very short tests with pauses in between. Using try and error approach, I found a return lead that brings the result pretty much exactly to 0.1 ohm. Now I should be able to simply change the trim pot for this setting so the fault light just goes out. But regardless of the trim pot position, the fault light always comes on. Either the pot is for something else or there is some problem in this unit. These are the 3 trim pots and they are pretty clearly marked. The most left one is for the soft 0.5 ohm range, the middle one for the long lead 0.5 ohm, and the right one, the one that I just tried, is for normal 0.1 ohm range. I had a look at the underside to see how things are wired, and came up with this rough diagram. It is not complete, the actual circuit is more complex, but it illustrates the principle. We have the big transformer here that provides 8 volts AC and up to 32 amps. One leg goes to the 2 power resistors and the other to the central earth terminal. In this drawing, the socket used is for the 0.1 ohm resistor. The current flows through the resistor, through the to be measured resistor Rx, and back through the earth terminal of the main socket. The 0.1 ohm resistor and Rx form a voltage divider. For example, if Rx has 0.1 ohm as well, the voltage at the socket in between will be 4 volts AC. This voltage is tapped by the green wire. It goes to the meter, which I did not show in the diagram, and to the PCB. On the PCB it connects to one of the transformers mounted on the PCB. The yellow wire from the soft earth return goes to the other transformer. It then gets complicated because the output of the 2 transformers are combined, rectified, and then drive a 12 volt relay, which in turn engages the earth fault light. Other contacts of this relay also disable the insulation test, which I did not show here. The rotary switch selecting between the 3 class 1 resistance ranges engages a specific 200 ohm trim pot, which can be used to reduce the voltage to the relay, thus allowing a higher Rx before the voltage is large enough to engage the relay. It is somewhat amazing that there are no comparators or Schmitt triggers or similar circuits. It just depends on the relay when it sees enough voltage to close the contact. Maybe these are special relays? Curiosity got the better of me and I downloaded the datasheet of the relays. These are from Panasonic. Of interest is the 12 volt version used in the earth resistance circuit and the 48 volt version which are used in the insulation resistance section. In either case, the part number indicates a single side stable version. It takes a maximum of 80% of the rated coil voltage to operate the relay. In our case, that would be 9.6 volts, but that is the maximum. It might operate well before that. The voltage may drop to the minimum release voltage, which in our case is 1.2 volts before the relay disengages, but of course it might also happen at higher release voltages. The word initial in the datasheet means those specs are only true when the relays are brand new. Also, the operating and release is assumed to be square pulses, again something not the case here. Lastly, there is this statement regarding that the operating and release voltages are influenced by mounting conditions and temperature. All in all, this means that the calibration of this tester has to be repeated every so often because the thresholds of when the relays close or open will change over time and temperature. As you have seen, the fault light in the normal setting is always on, even though the resistance is well within the green area. Further, the trim pot for this range doesn't do anything. It turns out both are symptoms of the same fault. This trim pot has lost its connection to the rotary switch and its lower leg is just floating. Because of that, it has no effect, and even the 0.05 ohm resistance is generating enough voltage to operate the relay. After carefully studying the rotary switch, I found that the yellow-black wire has indeed come loose. It's kind of tricky to see. Measuring continuity from the loose end, it connects to terminal D, and you might be able to see that the trace from terminal D goes directly to the trim pot marked as 0.1, that is the normal range. I used my boroscope camera to confirm that A, there was a tag at the rotary switch with nothing attached, and B, that it showed signs that something had been soldered to it before. This was very good news because I was afraid the tag had broken off, in which case reattaching the wire would be much harder. My other fear was that the tag showed that it was never used. That would have meant that the loose wire should join a wire at some other tag, and finding which would not be trivial. As it turned out, the repair was very difficult anyway because the tag is at a place where it's impossible to get to with a soldering iron. In the end, I decided reluctantly to loosen the rotary switch from the front panel and carefully position it to allow me to solder. This was very tricky because of the risk breaking other wires, but in the end nothing bad happened. And now comes the big moment. Yes, success, green light. Now the only question is it now too tolerant? To test that, I extended my long earth connection wire so its resistance is now above 0.1 ohm. It is now well in the yellow area, reading about 0.14 or so. In the normal setting it should be a fail, but I still get a green light. I gradually changed the trim pot while testing. Sorry, I missed that the camera was set so low to miss the trim pot, but as I get closer to the correct setting, you can see how the fault light comes on shortly and then turns green, and eventually it just stays on fault. Changing back to the cable configuration that had 0.1 ohm resistance, and it shows first fault and then changes to green. From the early adjustment, this behavior means it's hard at the threshold, which is okay for 0.1 ohm. Well, I think this will have to do. I can't adjust it any better. I closed the unit back up and I thought I might actually do a real class 1 test. I have this desoldering pump with an integrated soldering iron. It works reasonably well, and with all items coming from the Far East, I had already verified that the earth was properly connected. But now I can do a much better test, including insulation at 1250 volts. I think the iron will survive, and if not, it's not really an expensive thing. Here we go. Slightly below 0.1 ohm, and it passes both tests. Excellent. I was about to end this overlong video when it occurred to me that I had not tested insulation fault detection other than with crude sparks. Does this even work? The handling of insulation fault is the job of the second part of the PCB. It actually consists of two completely separate circuits because, as we have already determined, that class 1 insulation test is using a different source from the higher voltage class 2 tests. It works similar on the earth resistance tests earlier, but it's much simplified. Instead of having to transform low voltage drops to drive a relay, we have now the problem of way too much voltage. So the circuit consists of lots of resistors in series to drop the voltage for the relays, which are the 48 volt types. There is the usual rectification and smoothing cap for each circuit. This area is for class 1 because it has far less resistors as it deals with less voltage. So obviously the logic is the other way around from the earth resistance test. If there is sufficient high voltage to operate the relay, the insulation is okay. If the voltage collapses because of bad insulation, the relay will not operate and the device and the test fails. Of note, there are no trim pots to compensate for the somewhat indeterminate relay thresholds. This means the insulation tests can only be a rough guide. To test what the unit will pass in class 1, I connect a fixture with a 10 meg resistors between live and earth. This is where the high voltage will be applied in a class 1 device. Okay, it passes. 10 meg is sufficiently high. How about 10K? That should fail. And it does. So insulation testing does work. I wonder where the limit between pass and fail lies. Let's try 1 meg. And it passes. I would have preferred that this had failed, but it is what it is. What about 100K? Hope that fails. And it does. Good. Next, I picked 510K, kind of halfway between 100K and 1 meg. Unfortunately, I only have a tiny 1/4 watt version for this value. It passes. Really? This is a pretty low resistance for such a high voltage. Let's see, 1250 volts over 510K, that is 2.4 milliamps, times 1250 volts is slightly above 3 watts. This tiny resistor will not handle this very long. Here we go, and there is its demise. It is now failed open, but the cracks are sufficiently close to allow arcing. This is how it looks at the tester. It first passes, but while the high voltage is still present, it flushes over, causing the insulation fault to come on. Okay, destroying a resistor is fun, but will the tester really destroy a class 2 device, like a charger or a similar item? Somehow I think you guys will not be satisfied until I try and see what happens. But this video is too long already, so this will be in a follow-on part. I know that this video moved a bit slow, and well done if you are still here. This is what happens when confronted with an unknown device with the potential of real damage and zero documentation. But part 2 will be faster now that I understand this tester and it is repaired and fully working. I can just use it to test the out of unsuspecting class 2 devices. I'm looking forward to it, and part 2 should be out in about 4 weeks or so. If you like my videos, don't forget to like and subscribe and help growing this channel, and consider becoming a Patreon. The link's in the description. Thanks for watching.